Very simple case of radiation analysis would be radiation between two surface enclosures. We have seen so far a more general case, which is three surface enclosures, and we see how the exchange between all the different surfaces has different paths. And your circuit looks much more complicated than what you see in here for a two-surface enclosure. A two-surface enclosure looks something like what you see in the picture here. You do have only two surfaces, A1 and A2, and temperatures are T1 and T2, and your emissivities are emissivity 1 and 2. And it is an enclosure, so it's a closed area, basically, a closed space covered by all these surfaces. And the surfaces are only two. If I want to write the circuit, draw the circuit for the two-surface enclosure, I'd be able to draw it the same way as I've drawn it before, except that this time it's going to be a little bit easier because there's only one path for the radiation to go. It's not that, for example, one portion of radiation from one will arrive in another path to another surface, and then another portion goes to another surface. It's much more simple here. So you start by saying, if I want to put the two radiosity nodes, I have how many surfaces? I have two surfaces, J1 and J2. And in between these two surfaces, I have my view factors, or the geometric resistance between the two surfaces. So that's how I write 1 divided by A1 F12, or A2 F21. They're the same. Then I would be able to say, okay, depending on what the types of surfaces are, either they're black body or not, then I'll be able to say that there is a resistance for the surface itself, which is 1 minus emissivity of the surface divided by emissivity A1, which are these two resistances here. These are specific to the types of surfaces, and those relate the J1, the radiosity, to the potential of black body emission, which is this node and this node here. And that's about it. There's no other path here, and that's why your circuit looks very simple. Usually the purpose is to calculate, for example, the amount of radiation from 1 to 2, the net radiation from 1 to 2, and if you want to actually calculate it using this circuit here, you could use it different ways. You could use, first of all, Q1 is going to be equal to Q2, or the radiation from 1 is going to only get to Q2. The net radiation between 1 and 2 is going to be the same, except that the sign behind the value that you get is going to be different. So the net radiation is going to be either from 1 to 2 or 2 to 1. So that value that you get, you're going to get a positive value, let's say, for surface 1, which becomes a negative value for surface 2, which means that the net is from 1 to 2. And for surface 2, because it's the receiving one and the net is more radiation to surface 2 than it actually radiates out, so it's going to be a negative value for surface 2. But in general, based on your circuit also, you will be able to see that this is your Q1, this is your Q2, and they're going to be actually equal because there's no other way for this radiation to go. So if I want to write the relation for radiation transfer, I'll be able to write it picking, depending on what nodes you pick, you can calculate the radiation exchange between the two surfaces. You could pick EB1 and EB2, and in those cases, well, EB1 is actually Stefan-Boltzmann constant T1 to the power of 4, and this one is Stefan-Boltzmann constant T2 to the power of 4, and that's why I have the relations here. So you could pick those two nodes, and in the denominator, write all the resistances between the two nodes, or you could pick, for example, J2 and EB2 and write this relation here, or you could pick EB1 and J1 and write this relation here. So that would basically give you all sorts of different relations that you could use in order to calculate your Q1 and your Q2, or basically the exchange between 1 and 2. This is much like what you saw in conduction heat transfer. Depending on what nodes you know values of, you pick those two nodes and you write the resistance between those two nodes. And here, for example, all the resistance appear in series, so it'd be very easy to deal with them. We have added up all the resistances here because the nodes are the two sides of the circuit. So the nodes are from the very left side, EB1, to the very right side, EB2, and that's why I've put all the resistances. But if you pick nodes in between, you're going to see that your resistances are actually going to be just one resistance here, another one here, or these two are the same. 1 over F1 to A1 is equal to 1 over F21 A2. This is based on the view factor rule that we covered before. This table gives you some of the relations for the radiation exchange between surface 1 and 2 when you do have two surface enclosures. And these are for surfaces that are not black body. These are diffuse gray two surface enclosures. These are typical surfaces, and that's why someone has already sat down and simplified those relations that we had in the previous slide and has given us these relations here. Does that mean we can't really do this ourselves? No. You can go to Appendix A to see the proof of the equation 13.24 here. It's not something you can't do on your own. So let's say if you don't really have access to this table, you could still use the previous slide relation and just come up with the radiation exchange between surface 1 and 2. These just save your time a little bit. Some of the simplifications have already been done here, and that's why you can just directly come here and use these relations. But be very careful what these are. For example, this is spheres here. And for example, here this is cylinders. Be careful with how you use these, but other than that, they're just ready for you to use.